In Chapter 11, we're going to find a protein motif, and that's going to involve fetching some data and using regular expressions, and then also trying to figure out a way to do it without having regular expressions, which is an interesting challenge. And so this is the MPRT challenge. If we look at that on the Roslyn website, has some nice background for what we're looking for. It describes a pattern of text using some syntax here that's very similar to regular expressions. And it shows here we're going to be doing something different in this chapter in that we're going to need to go to the Uniprot website to download some data in FASTA format, and which we've already seen several times. And it gives us some background on how to do that. And then once we have these sequences, we're going to be looking for this protein motif, and it shows us a sample data set is going to have we're going to have these inputs of the sequences that we're going to need to fetch from Uniprot, and for each one of these sequences, we're going to output a list of positions where this protein motif can be found. So these are the things we're going to talk about: how to programmatically fetch data from the internet. I'm going to show it to you both using just some bash commands, some regular Unix commands, and then we're going to translate that into Python. And then we're going to write a regular expression to find this motif. And then we're going to talk about a way to find it without using regular expressions. So to get started, go into your directory here. Make sure that you source the virtual environment, then activate. I'm going to do that in 2 windows because I like to work with a REPL a lot of times. And then I'm going to go into the 11 MPRT directory, and you'll see I've already got a solution here. I've been playing around with this to make sure I know what I'm doing. And so the first thing I'm going to do is I'm going to copy the solution to the first solution to the name of the program that I want. I can run PyTest just to ensure that it passes all the tests that I have, and it does. So this is the way that the program should work. If we run this with -h, then we will see some help for how we want to write this. And this is a little new here. We're going to have an optional directory here that is going to be the directory where we're going to put the files that we download. And it's going to have a reasonable default. It's going to be called FASTA, which is a nice generic name for where we're going to be putting FASTA files. And then we're also going to accept a file here that's going to be an input text file with the Uniprot IDs that we're going to be downloading. So you should know how to write that. If you want to jump ahead, maybe use new PY to start a new program and get your program to do that much. But I'll show you how to do that here before I ask you to write the rest of the program. If we look at the input file under tests inputs 1, you'll see it's exactly the same input as shown on the Roslyn website, these 4 Uniprot IDs that we want to get. And when we run this, it produces exactly the output that the Roslyn website wants us to produce. So let's just run that and ensure ourselves that it does. Tests inputs 1.txt, and it does indeed return that output. And that ran very quickly for me. The first time you run it on your system, it will probably take a few seconds because it needs to go download those FASTA files. But if we look here, there is a FASTA directory, and if I look inside of it, there's a bunch of sequences. I've actually been playing around with some other tests and such. Let me get rid of that FASTA directory and let me run it again, and this time you'll see it takes a little bit longer because it has to go fetch the sequences, but it should eventually give me the same output. And there we go. And now if I do ls of that FASTA directory, you'll see it just has the 4 sequences that I'm looking for. So let's look at the FASTA files real quick. If we do a head, and I'm just going to do -2 to see just the first couple of lines on each one, you see here it wraps on. They're rather long lines because that this is real world data here, and you see that the header line for the FASTA file contains a lot of extra description Remember that in a FASTA file, the sequence ID is just up to the first space. So between the greater than sign and then the first space, that's the sequence ID. After that space and any number of spaces, anyone can put anything they like in that, and sometimes those lines, the description lines, will get quite long. So this is showing just the header and then the first line of sequence from each one of the files that we downloaded. So that is the data that we're going to be looking at, and I will be using seek.io to parse that. You don't have to, but it certainly is convenient. So how do we get started from scratch? Let's start with new PY, and we have our new script, and it looks just the way it normally does. And let's start bringing it. How do we write this? So the first thing that we want is some sort of a file and a download directory. So I've already got a type here for file. I'm going to move that to the top, and then there's going to be a second one here called download dir that I want to just have as a string. So I'm going to say download dir, and I'm going to get rid of the other two arguments that I don't need. And so here, when I go through my defining my arguments here, this is just going to be called file, and I am going to just run over here, and I'm going to open up my solution so that I don't waste too much time, and I'm just going to copy my definition here for the arguments, and we'll talk about those. Let me paste those in and get rid of the rest. And then let's just talk about this. So I'm going to have a positional argument called file. It's going to be an input text file of the protein IDs. And I like to make sure that the metavar says file, so it's very clear what I'm using. I am going to continue to use the deprecated argparse file type because that was the way the book was written, and that's the way the tests are all expecting certain error messages that come from that. I will, at the end, probably record one video to explain how to update your programs to not use that. It's going to have to get into using exceptions, which I don't feel like talking about right now, and so we'll talk about how to get around that. But since this is the way I wrote the book and the tests, I'm just going to leave it the way it is. I'm going to update this. I like to say file equal args file and download dir equals download dir. That's perhaps really kind of going a little farther than I need to, because I could just use the positional arguments here. There's only two. It's kind of hard to get those wrong. And these are very clear what they are, but I just like to I prefer actually to indicate the keys there for the name tuple argument. So with that, I now have a decent bit of code here. In fact, I can even use this code here that's default with new PY, where it's just going to iterate over each line in arg's file and print it. And let's just prove to ourselves that works. If I'd say tests input 1.txt, it actually does that. It does exactly something very useful with only having a few lines of code. And so let's just talk about that for a second. Also, let's run PyTest. And at this point, we should actually be passing. Let me run with -v so I can see. And we'll see that we're actually passing 3 tests already. We got the program to exist, it prints a usage, and it actually blows up on a bad file. Let me just convince you of that. If I say foo, then it says it can't open foo, no such file or directory. Nice error message, and that is exactly the error message that my test is looking for, which is why I don't want to change this from argparse file type right now. So with that, we have something that prints the lines of the input file, which is the first thing that we need to be able to do in order to go download those sequences. I show here in the book a different way to write this. First off, they're not just lines in this file. Each line is actually a protein ID. So saying for line in arg's file is a nice generic way to start off. but really it's better to use descriptive variable names so for when we come back we understand, oh, these are protein IDs that we're reading from this file. And so if I change that, my program still runs. I always like to just make a few changes and then run it again. And we see here, I've talked about this before, as we're reading each one of these lines from the file, it still has the new line attached to it that defines the line in the file. And so in order to not, if we don't have this end equals, what you'll see is that we actually have two lines between each, because print itself wants to add a new line. So we need to either remove the line, which we could do with rstrip here. That would be one way to remove the line. Or we could do the end equals the empty string, which we saw before. Because I need to rstrip every single one of those, I want to show you a handy way we could do this. One way we could do this is to write this as for protein in, and then we could say ID, well, let's say PID, because ID is actually a Python function, so I don't want to use ID. PID for PID in args file, PID rstrip. And we could use a list comprehension here to get rid of those. And that's quite verbose. A shorter way to write that would be to use a map. And the function that we want to call is string rstrip. And we want to call this as, we don't want to call the function, we want to refer to the function itself. And so if we run this, you see that also works. And I want to show you something real quick. If I go into Python and I have a string like foo with the new line on the end, that's fine. And I'm gonna put it into let's call it let's actually use one of the protein IDs. I'll take this first one and I'll see prot ID is equal to this string. And so I can say prot ID dot rstrip to remove the new line. I can also use string rstrip and I can pass it the protein ID. So string is a class. If I say help on string, this is the class of string. And the string class has a function in it called rstrip. And I can call the function and pass it a string, and it will do the same thing as calling the rstrip method on the string object. And it's all a little bit confusing if you've not had a background in object-oriented programming, and I can appreciate that. But what's going on here is that the function that I'm using for map is the function from the string class. And I'm not calling it, I'm passing it as a reference to the function. And the function will basically take this, and map will take the function and then provide the protein ID as the argument. And what we'll get back is the protein ID that has been stripped in the new line. So that's what's going on here. This is a slick way. I use this quite a bit to remove the new line from each one of the lines in a file. I will also point out that we could do something like read the entire file into a string and then call lines on it. Let's split lines. So if I have, say, something like foo and bar and baz, and I call split lines, then I get back the three lines of text here without the new lines. That's great. But what if your input file is 30 gigabyte in size? You don't have probably the memory, and it's an extremely inefficient way to read an entire file into memory and then try to split it, which would then actually make a copy of the entire file as lines of text instead of one giant string of text. So this is only acceptable if the file is small enough to fit into memory and in fact can fit into memory twice. So this is not a great way to go about working with huge genomics files, so don't do that. So with that, a lot of background on how to. So the next step in writing our program, now that we're able to read through the input file and get the uniprot IDs, is to, let's just construct the URL that we want to be fetching. So we have here this URL, and if we go look at this real quick, let's just open a browser, and then we take our first protein ID. Let's see what that one was. Just take this protein ID and we paste it in. Then we see that Uniprot gives us this really nice page with lots of information on it. And there's a bit of text that we want off here. We want the FASTA text. Wow, there's really a lot going on here. And you would be, so there's the sequence here, and we want to get the sequence for this. And it would be very difficult to parse this out of this page. But there's something that's really nice here that it shows us that if we take that Uniprot ID and just append the .fasta to it, that we'll get back .fasta. We'll get back a FASTA file with just the sequence, which is exactly what we want. So we're going to use that. This is the URL that we want to construct with our protein ID. And we can do that with an F string. So instead of printing the protein ID, what we want to do is I'll just take that URL and I'm going to paste it in here. It's going to be an F string, and instead of this hard-coded, it's going to be prot ID, like this. And if we run our program now we get back 4 URLs, and we should, I found a problem here. When I was testing everything for my videos, that worked just fine. But then when I tried this one, it didn't work. And it's because Uniprot and the Roslyn page still has this too, giving these as the protein IDs, expecting that this is going to work. But at some point, Uniprot has decided to not support this version of the accession. So it's saying that this is an invalid Uniprot accession. And it didn't take very long for me to figure out that they're just not happy with this extra information. They want it to be just the first part, basically everything up to the first underscore is what they want here. And so there has been a change since I wrote the book, since I don't know when they made this change, but we're going to have to modify the program as it's written to just strip off the Uniprot ID from the protein ID. So it's not difficult to do. It'll just be a small change to our program. So I want to first show you how you would go about getting this in just on the command line, because first off, it's a useful skill to have, and second off, we can translate this directly into some Python. So there is a program called curl, and you may have to download curl and install it, but on most Unix systems it will already be installed. And so if I take this curl command and I take that first FASTA URL and I run this, what happens is I now have a file called A2, let's see, and so I was a little confused here. There's a mistake right here in the book. That should not be dub. It should be rest.uniprot.org, which is the first. Here, if we run our program here, this is the URL that we want to fetch. And so if I say curl on that URL, then it gives me back the text, exactly the text that I want. And so I have a couple of options. I can either on the command line redirect that into a file, or I can use the -o option here, which is quite nice. And so if I rerun my program with this -o option, then it gives me a little bit of output there, and now I should have this A2 FASTA file. Very nice. So there's another tool that we can also use, often already installed, but you may have to install it, wget for WebGit. And if you don't know about these tools, I recommend that you get familiar with them. They're extremely useful. And so I can also run this exact same command with using wget. prove to you that wget, and actually I may need to, yep, it actually, it saw that there was an existing file, and so it actually wrote it to a backup file, which is very handy. It's nice of the program not to override existing data. You can really shoot yourself in the foot with doing things like that. So it doesn't matter which tool you want to use, curl or get, but it saves you a lot of work if you know about those. And so I want to just take a second to show you how to write a bash script that will go and download these files. And I have, let's see, first off, let me clean up my directory here. I don't need these files. And I have given you this shell script here. It certainly looks very foreign from Python code, which is entirely the reason why Python has the syntax it does. But in shell, we use a lot of these sigils in front of the variable names, which is where Perl gets this from. I did a lot of programming in Perl, and so variables are interpolated by putting these sigils in front of them. And I have here just a little bit of trying to print a usage statement on how to use this. So it's going to accept, it's looking for a file of input, which is going to be in $1, and it's going to use a while read loop to read in each line from $1. This is the way you read in a file. And it's going to put it into a variable called protein ID. And here I had to add in a little shell call to sed to get rid of everything after the first underscore. And then it's going to echo that protein ID. It's going to construct the URL. This actually, I think, needs to be rest.uniprot. Interesting. I feel like a couple things have changed here. And then I think this actually works. So we're going to give it a little try here. It's going to echo the URL. It's going to say that the output file is going to be in this output directory, which is going to be FASTA. And this is some very confusing language for if the directory does not exist. So -d is a test for directory. And that will say return true if it does exist. And I'm going to negate it with an exclamation point, which we often call bang. And so if it's true that it does not exist as a directory, I'm going to call makedir on that. And so that way, when I define my out file as being the outdir/proteinid.fasta, and I'm going to call wget on the URL and writing the output to this output file. And then I'm going to print a little message that I'm done at the end. And just to prove to you that that works, I'm going to get rid of the FASTA directory that I currently have. And this is what my working directory looks like right now. So if I say fetch FASTA, it wants the input file. You see there, it gives a little usage statement, just like a good program should. And so it's printing that. It's printing the URL that it's fetching from. And you can see the progress as it's going along. You see here it has stripped off the extra bits from that. And if I do an ls-l on my FASTA directory, you see that I have text in all of them. I can do a head-2 on my FASTA files, and it looks like I got the data I wanted. So it is useful to know how to write bash. This is probably about as long of a bash script as I would want to write. Even this has a lot of potentials for writing it incorrectly. I would probably prefer to do this in Python, but it's good to know how to do this. And I would encourage you, if for every line, for every bit of syntax here that you don't understand, you should really go learn, especially tools like sed and awk. That can be incredibly useful, can save you hours of writing Python when you could probably just write a little sed or awk script to extract some data. So knowing how to do this in bash is useful, and we're going to essentially translate this directly into Python in a moment. So if I write that, I now have my input files, and I could run my MPRT on the next step, which is I've now downloaded the FASTA files. And so the point of that was to get at the FASTA sequences. So now that I have those, I could go on and do it. But the first thing, before we go that far, I'm going to now show you how to write that same idea in Python. So, if you wanted it, You could have a separate step that's just a bash script that runs to download the sequence files, and then you're just going to write the Python to analyze those. But I'm going to go ahead and show you how to do the same thing in Python. So to get started, I'm going to add to my program here, MPRT. I'm going to create a function called fetch FASTA. And this is a nice way to start off here. I'm just going to go copy this and make it look nice. And so the way I want this to work is that it's going to take a file handle, which is this text.io, which is the input file that we have up here that we defined as the file type. So that's going to be, if you'll remind yourself up here at the top, it's going to be this text.io, which is a way of representing an open file handle. So it's going to take this text.io file handle, and it's going to take this FASTA directory that is where we're going to download the FASTA files into. And this is where we're going to be defining with the download dir, and it's going to have a default value. So the user doesn't really have to give us anything. We're just going to, by default, put it into FASTA. But if they want to override that with some other, we can. And so the way this is going to work is that it's going to fetch FASTA is going to return. Right here, it's going to return a list of strings, and those strings are going to be the files that we just downloaded. And perhaps there's a bad protein ID in the input file, and we're not able to download it. So we're only going to return the files that we actually created. So that's going to be important. So this is how I want to be able to call the program. And I often write code like this. So instead of writing this for protein in args.files, I'm gonna get rid of that for the moment. And this is the way I would like my program to work. And and I'm going to challenge you to go try to write this without looking at the way I did it. I've shown you how to do it in Bash. See if you can challenge yourself to write that in Python. And I'm going to say that I use the OS and the sys modules, and especially I use this module called requests. And if I open this, I highly recommend that you read all about the requests module. It's extremely useful for making web requests inside of your Python code. So, there are many ways you could do this. You could actually, even from inside Python, just make system calls to curl and wget. And that would be a way of downloading the files. You would just say exactly those same shell commands that we put in a bash script. You could put them and call them from inside your Python, and that would be a way of downloading the files as well. Requests is a built-in Python module that you can use to do that with Python syntax and not calling out to external programs. So however you want to go about it, I challenge you to download the files and print them. Print the names of the FASTA files that you downloaded. If you are still with me here, I'm going to go ahead and show you how I wrote this program. And to bring this in, I'm just going to copy it. First I can save. I'm going to copy this from my first solution because it's a little bit complicated. Excuse me. I'm going to copy this, I'm going to paste it, and then we're going to talk about it. So it is extremely similar to, and in fact I'm going to pull up, it's extremely similar to the bash script. So let's just look at this real quick. I define this output directory. That's the FASTA dir here that's going to be. And this line here, if the output directory doesn't exist, then make it. That is what is going on here. So I've already talked about os path isdir is a function from the path module that we can use to say, is this directory, does this exist as a directory? If it's not true, then I'm going to call os make dirs. And I have a couple of notes here about make dirs. One is that this could fail. It could raise an exception if it's not able to go out to the operating system and make a directory. Make dirs actually makes all the directories. That's what's going on with make dir-p. So if the user said, actually I want the data to go in /opt, my username, /data, /project name, /FASTA, then there would be all these parent directories that would need to be made along the way. And so makedir by itself will only make one level of directory, and if there are multiple levels, then we need to pass the -p, and I always pass -p because I don't know what outdir looks like. So makedir -p will make all the parent directories. That's what OS makedir does. There's another function in OS that will only make one level of directory, and I never use it because I don't know what I'm going to be getting from the user. I have a point here though. It could crash. It could raise an exception. Could crash your program. Very simply, maybe the user is trying to create a directory and write into a location where they don't have permissions to write, and there's really nothing my Python program can do to fix that. And so, to my mind, just let the program crash. Just let the exception be raised and the program falls over, because there's no way my program can fix that. Some human's going to have to intervene and fix the permissions problem, or they're going to have to change the argument. So that is generally what I do. Is I don't want to get into exception handling and writing complex programs. Let it fail. And so moving forward, while read protein ID, this is basically our for loop here. I'm creating a for loop to read through our file handle. I'm doing the rstrip little trick that I showed you before. And this is something that I had to add since publishing the book, that I take this protein ID and I'm going to go ahead and use that for the file name that is in every other place in the program. I'm just going to use that same protein ID because that's the output that the Roslyn page expects, and that's the way that the tests were written. But in fetching the uniprot ID, I'm going to have to look for the presence of an underscore. So the first thing I do is I copy protein ID into uniprot ID. And I say, if it's true that there's an underscore in the protein ID, and so let's just look at what that looks like real quick. Let's take let me cat the test inputs 1.txt. Let's take this one, and let's go into our handy REPL, and I'm going to say protein ID is equal to this string, and I want to say, is it true that there's an underscore in protein ID? And it's true. And if protein ID were equal to this, then that would return false. But we're going to deal with the one where there is a underscore in that. And we can actually call this method called protid.split, and we can tell it to split on the underscore. Now, if I'm being a little extra safe here. This does not have an underscore in it, but if I say split on the underscore, I'm still going to get back just the first part of it, which is kind of weird, but I guess handy here. It at least won't blow up. So split is a little funny that way. I'm going to go ahead and go back to this version of it. And if I say split, then you see here it has split now this string into 3 strings, where every place where there's an underscore, it broke it apart. And I just want the first one. And technically I don't need to run this if underscore, this test for the underscore, because I could, if I run this here, let's just say uniprot ID is equal to that, and I'll prove to you that uniprot ID is not fine. Sorry, let's see. I first copy uniprot ID to protein ID. Let's try that again. And then I run this line, and I say, what is uniprot ID? It is just the first part of this identifier. Let me go back real quick and just prove to you that if it's like that, let's see, uniprot ID is equal to that, and then uniprot ID is equal to that, I can see that uniprot ID is indeed just the first part. So either way, however I want to get about this, I need to get the uniprot ID to be just the first part of that. So going forward, I've had to make just a change here that the URL is going to be using the uniprot ID, the one that I've stripped off, and not the full protein ID. I decided to go ahead and use the full protein ID for the name of the FASTA file that I download, and the rest of the program. So that's the way I wrote that. So otherwise, if it's this also has an advantage which I didn't write in my fetch FASTA. I always do the wget here. I don't bother to see if the output file already exists. So every time I run fetch FASTA, it's going to run this. And there's a simple test here I could add of, it's basically this exact right here. If not -f out file, out_file, then I run this. So I could have written that. That's actually better. And so it won't run wget if the output file already exists, and that's exactly what I'm doing here. There's no reason to fetch the FASTA file a second time. If it already exists, then I just jump to this line here, and I append the FASTA file, the local FASTA file, into my files that I'm going to return here. If it does not exist, I create my URL that we've already been seeing several times, that we've been playing around with, and then I'm calling requests get. And if you are wondering why it's called get, it's because there are these verbs in HTTP. We get, we post, we update, delete, and so a get request is a particular kind of request in the HTTP hypertext transfer protocol. And so we're calling a get request on this URL. And we expect to get back a 200. If you're not familiar with return codes from the web, perhaps you are familiar with a 404, which is what happens when a resource is not found. And so 200 is generally of the success class. 200 is not the only one, but it's the most commonly used status code to say that the request was successful. And so if the request was successful, then in the response, we're going to have some text, and that is the FASTA file. And so we want to print that text into the file that we're going to open. We're going to open the FASTA file as for writing, and that's where we're going to print the response text. All very concise way of getting Python to download the FASTA files and to write it to this output file. And in the case where the status code is not 200, we're going to print an error that we had trouble fetching this URL. We're going to print the status code, and we're going to print that to standard error. Always a good habit to get into, to print your errors to standard error. In order for this code to work, I'm going to need to pull in the OS module and the requests module. So let me do that real quick. Let me jump up here, import OS and import requests, and let's see if we are able to run our program. Let's see, mprt on tests inputs 1.txt, and oh, it does not like that I'm missing list. Let's add that. And what else? Looks like it is probably working. No news is good news. So it has now printed the names of the files. And let me just get rid of let's just run that one more time. We'll get rid of the FASTA directory. Run that again. And we'll prove to ourselves that this did work, because those files already did exist from having run it before. So we see here, I called fetch FASTA on using the input file of IDs that we have, and I told it to write into the the download directory, and it returned a list of files that I then printed by joining them on the new line, which is what we see here. And if I ls-l in my FASTA directory, I do see that the files are there. If I head -2 on FASTA star, I see it looks like I got the data I wanted. So that function works pretty well. And and it's hidden away in a function, so my main doesn't get too cluttered here. So far my main function is just 3 lines of code, getting the arguments, fetching the FASTA files, and now I can move on to the main part of the program, which is actually looking inside the FASTA files to find something interesting. So we've spent all this time and we haven't really gotten to the meat of the program, which is finding this motif, we've had to do a lot of plumbing essentially to get our data into order so that we can actually find the data that we're looking for. But all that is a crucial part of bioinformatics, is preparing your data and cleaning it up and making web requests. And so now you know a couple different ways to how to do that. So let's move to the next part of our assignment here, which is to write a regular expression to find the motif. And I'm definitely going to start with a regular expression because everything about the way that the program is described just screams for regular expressions. For one thing, we have this note here that what we're looking for is a protein motif that's represented by this, what they call a shorthand, which is just a kind of syntax where this XY inside square brackets means either X or Y, and in an X inside curly brackets means anything that's not X. So the motif we're looking for here is an actual N followed by something that's not P, followed by something that's either an S or a T, followed by something that's not P. And then I point out here that the ProSite website, which I pulled up here, is an interesting resource that they also have the same kind of information where they describe their motifs using a language like that, and it all just really screams for a regular expression. So in the typical regular expression syntax, this is the way we write this. N is just a literal N is just itself. The way that we say anything not something is that we put we first off create a character class, which is what S or T is, which is a character class saying it can be either S or T. So we create a character class for P, and then we negate it by putting the caret sign in front as the first character inside the character class. So we can actually put other characters in here like P and N or X or whatever. It'd be anything that's not that character class. So this is a character class and this is a negated character class. So very clean syntax. This is the motif that we are looking for, written in regular expression syntax. Another way that you could maybe think about this, I find this quite soothing, is a finite state machine representation where we see that it's something that's in, something that's not P, and then there's this graph here that it bifurcates here. So from this node we can either go the S route or we could go the T route to get to this node, and then as long as we find something that's not P, we make it to the N, which is this double circle. Very computer sciencey way of representing a regular expression, but it may help you to see how the text that should match how we can find it. So we're going to do this with the regular expression module, and for this I think I probably need to I'm going to create a new, I'm going to go into my work directory, I'm going to source v&v bin activate, and then I'm going to create another REPL here in case I need to use any of the modules that I've got. So the first thing I'm going to do is I'm going to import the regular expression module, and I'm going to use my the compile function to put that into a variable called regex. Very important that I do not put it into a variable called RE, because then I would be shadowing the RE module and it would break everything else. So now I have this thing called a regex. What is the type of regex? It is this something called an RE pattern. So RE, the RE module inside of that is some sort of a object called a pattern. And if I want to know what can I do with regex, I can call help on that, and it returns all of these functions I can do, like search and split and sub. Extremely useful to know how to compile a regular expression. So now it's this object that I can use over and over again, and the expense of turning this syntax into an actual regular expression has already been done, and now I can use that cached data, that cached state, to actually do searches. So it's very useful to know how to compile a regular expression and use that. So for instance, if I have this sequence where the motif that I'm looking for is actually represented twice, let me put that there, I can call the findAll method. So we've used findAll before, but a lot of times we were using, like, for instance, I'm going to use RE findAll, and I'm going to pass it the regular expression that I'm looking for, and I'm going to say I'm looking for it in seek. And so it's essentially doing the same thing, but and I've talked about partial binding a little bit. It's kind of like I've partially bound the pattern. It's this part of compiling this into a regular expression and then calling findAll on seek has already been done. Once I've compiled this, I'm just going to call regex findAll on seek, and I get the same answer. So if that's confusing to you, I would ask you to sit with that and try to understand. It's a little bit like the idea what I showed you before of saying foo.rstrip. That part was already, the string has already been already attached. It is the string, and calling rstrip like this on foo new line, and we just get back foo. So these are just getting comfortable with how to use functions, and sometimes the functions are already attached to an object, in which case they're called methods. That can be definitely something that's confusing about object-oriented programming, but you will see the code written in two different ways, but it's all functionally doing the same thing. So with that, this is a way to find all the pattern that we're looking for in seek. But the problem is that the sequence contains two copies and they overlap with each other. And we've already talked about this in chapter 8, is that that writing it in the normal way totally misses these overlaps, because once it finds the pattern, then it starts the next search from where it ended and goes on. It doesn't find the second one. So we already talked about the way to get around this is to put it into a look-ahead assertion. And the way to do that is to wrap the pattern in this question mark equals, and then put parentheses around it. So this is another way, a better way to write our pattern. And now if I call regex findAll on the seek, now I find it in two different places. That's pretty much all of the work done for me. From here, I've now handed you the keys to finding every occurrence of this regular expression in a sequence. So I would challenge you, stop the video and use bioseek.io to parse each of the FASTA files and look for, in the sequence, use this regular expression to find all the locations. So what we want is the location, the starting from 1 in the sequence of where the motif can be found. So hopefully you're spinning here. We've already gone over a number of things in previous chapters where we've used something like this, and we need to find the positions where these things are. So if you're sticking with me here, I'm going to show you how to do that. So the first thing is that we've talked about find all and find iter. Find all is great, but it doesn't give us the positions of those things. And so there's another method called find iter, which calls this iterable object, which you know that we've seen this before. So we could force this into a list, and we see here that it is actually returning two match objects. And inside these match objects, it's just, this is a string representation to try to help us to understand what's in there, but it is telling us that it's spanning from 0 to 0, and then there's a span from 1 to 1. Those are the positions. That's what we need right there. And so another way to get that would be to say match for match in, and then let's just call it that. And that's exactly the same thing. I'm using list coercion here, and here I'm writing a list comprehension, but it is a way of getting the match, is to iterate over the matches. I point that out because there is a match start argument, a method that we can call here. So instead of calling match and having it get a string representation, what I actually want to do is call match start. And those are the places in the string where it can be found. Unfortunately, the Roslyn expects us to give 1-based positions, not 0-based. So we can correct that by simply adding 1 to those. And so those are the positions of our regular expression, of our motif. And that really is all you need to finish writing the program. I'm going to again encourage you to stop the program, stop the video here and write it yourself. And I'm going to keep going and show you how I went about doing that. So the first one is, the first way I wrote this using regular expressions is I'm going to compile that, my regular expression. And the first thing I need to do is jump up here and import regex. And then I can go down here. I can put it, I'm not sure, let's see how I did this. I got my files and then I compile my regular expression. I like that. And instead of printing the files, I'm going to get rid of all that. Now I'm going to iterate over each one of the files. So for file in files. And I could start off by just printing the file. Let's just do that. And let's run our program, not tests. It's called nprt. And I'm going to call test inputs 1.txt. Make sure that I've got, let's see, no, not regex. My apologies. It is called re. So again, I just want to make just one small change at a time. I don't want to bring in all of this code, and I want to talk about this. So the first thing I'm doing here is the name of the file. I want to get this part out of this. So this is telling me where the files are located, and this right here is the protein ID. I want that piece of information. So let's take this for a second. This is going to be the string that we're given. And we're going to call, say, file is equal to, sorry, put that in strings. There is, I'm going to import the OS module. There is something in import, in OS path, there's a function called base name, which I use all the time, and it will return, it strips off the directory. Any leading directory information strips that off and just gives me the base name. There is also a function called os.path.split extension. And if I give it something like the base name, it will split that file, that string into the first part and then the extension. And in the way this works, it's going to include the dot at the beginning of the extension. So what I want is to call split extension on the base name of the file, so that I get, I'm trying to get just this piece of information. And because that's actually the only piece of information I want, I could just say, well, just subscript that down to the 0th element and just give me just the protein ID. The file stem is another way of talking about that. So that's what's going on here. There's two different ways I could do that. So I could do that, or if I call this, I could say, I'll just call this root, and then this other throwaway variable. And so now I have assigned root because split.ext returns a tuple, right? And so I'm assigning the tuple to two different variables. I'm unpacking it. And when I unpack it, the second one I'm calling underscore, which is just a throwaway variable name. It's actually a valid variable name in Python. And it especially has the side effect of letting linters know that you don't intend to use the variable, which is important. And that's what's going on here. One way I could unpack this is I could say the protein ID, I'm assigning protein ID, comma, underscore to split.ext on the base name so that I can get the protein ID. So that is what is going on in this first line. You take that, and I'm going to put that into my program. So instead of printing the file, I could write it like this, or I'm going to say I could also write it like this, where I'm only taking the first bit and assigning it to protein ID. taking the first member of the tuple that's returned by split.ext. The next thing I'm going to do is I'm going to parse the sequence file as a FASTA file. And for that, I'm going to need to from bio import seq.io. And that should be in your virtual environment, should not have a problem bringing that in. Now, seq.io parse is going to return this rex, and I want to stress that that is a lazily evaluated generator of the sequences. So you might be tempted to think that I have now parsed this entire FASTA file into this data structure that has potentially millions of records in it. Actually, it's just a generator, and it will only produce the records that I actually expect it to produce. So one way of writing this is if it's possible to get the next record from rex. I've shown this before, this next, then it will produce the next record. And let me just show you how that looks from bio import seq.io. And let's take that line real quick. And let's say, oh yep, file is still set to that. So if I say rex is equal to this, let's see, no such file or directory. I may not be, let's import os real quick, and os.lister. What directory am I in? Oh, I'm not in the, it is in my, sorry. It'll be easier if I just go into my 11 directory and try that again. So import re and from bio import seq.io. And this is my file. And then let's do this again. We should parse this. Sorry, I typed that wrong. It should be file. Okay, now if I say, how did I call this here? I want to make sure I'm using the same syntax. Rec. So rec and rex. Rec is going to be equal to next of rex. And rec has a sequence record, and we've seen this before. I've called next because if I look at what rex is, what is the type of rex? It is this FASTA iterator. We've seen this before, and so it being one of these iterators, we can call the next function on it to have it produce the next record that we have. And so this is one way of iterating over this because actually there's only one record in there. I don't need to iterate. I don't need to do a for loop on this. I'm only expecting there to be one record. So I'm saying if it's possible to call next on rex and it returns something into rec, and then that is something, there's actually something there, that's the only record I care about. So I'm just saying, give me the next record, and I'm only going to do that once. So I'm just reading the first rec, and then the first record in the sequence, and then I'm skipping. So you could come up with another way of just reading the first record, but this works. So I'm going to take this idea, I'm going to put this in my program. And so if I get this next record, I want to see if I can get the matches on that. So we already looked at a find iter. We've compiled our regular expression here. That's the regular expression, and we're calling find iter. And we want to pass it on the string. So if we look at rec.seq, what we have here is this string object. We've seen this before. And what we want is a string we just want to force it into just give me the string. Just give me the actual sequence. So that's what's going on here. I'm forcing the record sequence into a string. I'm calling regex find iter on that string, and then I'm forcing it into a list, which we saw before, what I was doing in the REPL. And if it's possible that that returns a list of matches, and I'm using the walrus operator again here, if I'm able to get something, a non-empty list, back from matches, now I have all the positions where my motif can be found. And so if it's true that I found some matches, then the first thing I want to do is print my protein ID, because that is what, if we look at the Roslyn website, we want it to print the protein ID, and then we want it to print these where it can be found. And then I'm using this, we already saw this in the REPL. I did this list comprehension for each one of those matches in my matches. For each one of those match, I want to print start plus 1. And this is a trick from the very first chapter, where I'm just splatting that list. So if you remember, it returns a list of integers, and I want to splat those in from not the list, but make the list into all of its individual pieces, and then pass that to print, and print is going to turn those integer positions into strings and print them for me. So that is what is going on. I print the protein ID, and then I splat all the matches, and I print those. And let's see what our program looks like if I run this. Oops, I don't mean to make that full screen. Let's run this. And instead of printing the file names, now it's printing the output that we expect. It's printing the protein ID and then all the positions in the sequence where our regular expression can be found. And if I run PyTest on this, then I should pass all of my tests while that's running. And so all of my tests have passed. So that works. That is a working solution for finding all the locations of our motif in our FASTA files. I have here a note about SplitExt, a little more explanation on that. And I just will note that bioinformatics can be really quite frustrating. You can find lots of different extensions that describe FASTA. Very common to see both FASTA, but also just .fa. You might see .fna for nucleotides, and you might see .faa if it's protein sequences. You could also see AFA for an aligned FASTA. Lots of different formats, and the extension may or may not accurately describe the actual data. So just because it says it's an FA file, you might want to head the file and make sure it's not actually a FASTQ file. So just be aware of that as you work with data. So I show a little bit more here about how to split off that first part that we're looking for. Okay, so let's just consider if you didn't have regular expressions. It's kind of like seeing if you could tie one hand behind your back and fight someone. How would you try to write this if you didn't have regular expressions? So as I was considering this, I thought, well, let me write a function. I tend to want to write functions where given some sort of a text, I'm going to return this list of integers that is going to be the positions where that can be found. Now the motif itself is going to be hard-coded here, so this is going to be what I'm looking in, and I'm not going to generically look for any motif. It's going to find a very specific motif. So this is how I decided that this would be written, and in order to help myself write the function, I wrote this test. And this is like truly the way test-driven development is supposed to work. You have some idea for a function. You basically define the function, and it does nothing. It returns, for instance, here, it's supposed to return a list of integers. Excuse me. And it returns an empty list to start. So it is callable, but it doesn't do anything useful. And then I go write a function that says, well, if I pass it the empty list, I should just get back if I pass it the empty string, I should get back the empty list, which is fine. And if I pass it the thing that I'm looking for, a string with not the thing I'm looking for, I get back, an empty list. Same thing here. But now when I pass it something that does pass, I get that it's found at position 0. Here it's found at position 1. Here it is overlapping, and I should find it in 2 different places starting at the beginning. Here it's overlapping, but it starts 1 character in, and then here it's found in 4 different places. And so, it's a pretty good test suite. It exercises the function in several different ways. And so I start by thinking, this is how I want my function to work. And this is a very silly thing to do here, in that the regular expression is clearly the way to write this. But I'm doing this as an academic exercise to say, if you are going to go off into a greenfield piece of code and you're going to start writing functions, how do you write functions and then test them? How do you think about how to decompose your program into these small bits that you can really understand and verify that they work? So that's all that's going on here. This is not actually what I would recommend that you do in writing production code for this particular solution. So we have a decent way of thinking about proving to ourselves that this function that we write will work. And the first thing that when I think about this, the solution here is going to involve finding formers, because the motif that we're looking for is 4 amino acids long. So I decided, well, I'll go back and use my find k-mers function. And what's nice about this is that I've already written a test for that, and I've already proven to myself that find k-mers will work. And so I can go pull in this function from previous work, and this is where you start to get at, wow, I keep using these same functions over and over again. Maybe I should have them in a module where I just write them once and I share them across my whole project or all these different projects. And I hope you are starting to think in that kind of way, and that's the whole point of creating modules and sharing code. So I've got this find k-mers. I can bring this in. I don't need to explain how this works. And so given this sequence, and I can jump into my REPL here, and I can run some of these. So from my solution 2, which is, if we look here, solution2 manual.py, from solution2 manual, I'm importing find k-mers. So if I say, I'm going to use this as my sequence where I know it overlaps, I can say find the k-mers that are formers. Find the formers that are in the sequence. Cool. Using that, I can now scan through these for ones that match the motif I'm looking for. I need to know where the k-mers are, though. And so one of the things that we've seen before is that I can call enumerate on that, and it returns this enumerate object. So therefore I need to call list, and that will give me the k-mer and its position in the string. So the first k-mer is NNTS, there it is right there, and then the next k-mer starts at position 1 and it's NTSY, there we see that, and then the next one starts at position 2, TSYS. That's exactly what I've got. So now I have both the formers and their positions. So I hope you're seeing how this works. I go through each one of these formers and each one of the k-mers, and I say, is this a match for the motif I'm looking for? And if it is, what I want is the first bit here. I want the start of that position. So one way to write this is to look at each position in the k-mer. So let's just take it and set it equal to the first k-mer here. And one way to write this, I can say, is if the first piece of the k-mer is at position 0 is the letter N, and the second letter is not P, and the third one is in the string S or T, and then the last one is not P, then that is a match. So let's just take that bit of code and verify that is true. This is our a match for our motif. And so I could write a for loop over this. Gets quite ugly, but for, and I'm enumerating the find kmers, and I'm unpacking it into I, which is the position, and kmer. Then what I want is, I want to print this line, and I can actually just indent this line. And so it's the first two are matches, and the third one is not. So this is the code that I want to stick into this function called isMatch. And so given a string, this is going to just return that, first off, that the sequence is 4 characters long. I want to make sure that this would blow up if I try to pull out parts of the sequence that are beyond the length of it. And so first off, I make sure that the sequence is 4 characters long, and then I run this bit here, and I return this, true or false. So this is a function that will tell me if the given string is the motif that I'm looking for. And again, it's nice to write a little function here to test that. If it's going to accept a string, I always make sure to pass in the empty string to make sure it doesn't blow up, and I verify that this is a match and this is a match, but that this is not a match. That is not a match, and this is not a match, and this is not a match. So a good way of writing, this is a decent way of writing some tests. So now I have a function that will tell me that I've found the motif I'm looking for. And so I can rewrite my, let's see if I can bring this in. Let me just copy this. I'm going to define this in my REPL, and in order to use it, I can't have this new line. It's a little frustrating. You know what? I'm going to, from here, I'm going to import the isMatch. I can also import that. And so I want to do that so that I can see this way of writing this code. So for each position and kmer, in enumerating the kmers, what I want to print is the position, the kmer, and whether or not it's a match. And so now, again, I can see the first two are matches and the third one is not. I hope you see how we're building up to our eventual solution here. I could take all the kmers, and that's going to return, I could force a list, so I'm getting back a list of all the kmers. Looks like this. And then another way I could write this is I want the position if the kmer is a match. So we've seen this before. This is a list comprehension that has a guard at the end. So it's only going to return the I for I and kmer in kmers if isMatch for kmer is true. So this gives me 0 and 1. Super handy. Another way, and we've seen this before, of writing this is to use the star filter from the iteration utilities. So I could actually combine this. I need to use star filter because the kmers it's a list of tuples, and I need to expand the tuple into I and S, which is the string. And so I'm able to write the same idea, get the same output from this using star filter, and then my lambda is able to accept 2 values instead of the traditional 1 value that the regular filter wants to accept. So that's another way of writing this. Yet another way of writing this, also using star filter, is so I get my matches back like this. If we look at what matches looks like, it's this generator here. But if I call it into this tuple, all I want is the first position. So given a tuple, I have to return this T0, which is the whole point of what I'm trying to get away from. So what I'm doing here is this is returning these tuples, and what I want is to only print the first member of those if it's a match. So I could define these functions for first and second, which I stole directly from Haskell. So given a tuple with anything in either position, just return the first thing and return the second thing. You do this so much in Haskell that these are just built-in functions. So another way of writing this idea is to say filtering for the things that are a match on the second part of the tuple, give me the first part of the tuple. That may or may not look completely like gibberish to you, but it is a very functional way of writing this idea. What I'm trying to do is go through the k-mers, find the matches, and if that's a match, I just, on the second part of the tuple, then return the first part of the tuple. Kind of cool. I like it. Or another way of writing this, and we've talked a little bit about, is a star map. So if I take this, I could get the same code, but this is going to be, this returned, the first time I ran this, I was very surprised. I wanted to see 0 and 1, and what happened is I got 0. And if we take this part and we try to understand it, what's going on is that I've talked about this. If I use filter of none, then it looks at this kind of identity function, and it essentially filters out things that are truthy and falsy. And so if we take this list here of 1, 0, and 2, and we filter on none, it removes the 0, because 0, if we look at the Boolean value of 0, is false. Whereas the Boolean value of 1 is true, the Boolean value of 2 is true. So if we coerce, if we use filter of none, then we're essentially applying the Boolean function to each one of these values, and so we don't get 0. It's like if I had passed in none here, I would also expect that to be removed, but you have to be very careful in Python when you're using these kind of tricks and these coercion of values. None seems like, yeah, okay, that's basically a false value, but 0 is a defined value. It's there. 0 is something that I want to see pass through my filter. But if I just filter on the idea of being truthy, of being not false, then I lose the 0. And that's what happens here when I filter this list on none. I need to be more explicit. I need to say, like not -1 or something like that. And so just something that's like a little side note that you need to be very careful about when you start using these ideas in Python. So to finish up here, I create this find motif. It's going to enumerate over the find k-mers to give me this list of k-mers, and I'm going to return I for each one of the k-mers that is a match. So I went down all that side road just to show you some ideas, but when it comes down to it, this is the way I'm going to write my find motif, and it works on using this isMatch function that we looked at. So if I just look at I'm going to copy my solution 2 to my MPRT, and I'm going to first off just assure myself that this does work, passes all my tests. Great. Let's look at this program, and what we'll see here, fetch, FASTA, all that is the same. What we care about here is the main. All this is the same. If we're able to get a record out of Rex, then we call find motif, and we say if it's possible to find matches on find motif, then we're going to get the positions here, and we're going to correct for 0 based by adding 1 to each one of our positions. And another way of printing this is to print the protein ID, and then a new line, and then joining all the positions on the empty string and mapping those positions through the string function, which we've seen before. This is another way of going about printing those 2 lines of text that we need, very much relying on some techniques that I've shown earlier. So just a real quick, if my positions were, let's say the positions are 0, 1, and 3, if I were to try to print, how can I print those? Well, I could present, if I print pause, then I'm going to get this string representation that has the brackets and the parentheses, and I don't want that, so I could splat that, and it just prints 0, 1, 3. If I try to join my positions on the empty string, it's going to blow up because it can't coerce the strings, the numbers into strings. So what I need to do is I need to map that into the string function, and now it's able to turn each one of the positions, the numbers, into a string representation that I can now call on join. So that's what's going on here. That's why I'm doing that join there. So a couple of different ways of doing this. The second way was really just to stress how to write functions and tests and how to decompose a complex problem into smaller problems. So going further, I point out another Motif database that you could go look at. You could write a program to search for those motifs in your given FASTA files. Review real quick is that I introduced curl and wget that you could use on the command line to fetch data, or you could write it in Python, or from Python you can call these programs however you want to go about, whatever makes sense to download data for yourself. I showed you how to write a regular expression to find the motif that we were looking for, and that again we needed to wrap it in a look-ahead assertion in order to find overlapping versions of that. The manual way that we did this iterated through the every position of the string, and so we didn't need to worry about that because we were manually looking at the overlapping positions. I did show that it's possible to write a way to manually find it. It's not recommended, but you don't have to look at regular expressions. And sometimes regular expressions may not be able to find the kind of string patterns that you're looking for. So it's important to know how to force it yourself, do something manual. We also talked about the split ext function, which separates the file stem from the extension. And I just point out that you should be aware that sometimes file conventions, the extensions are maybe unreliable way to describe what's actually in the files. So I hope you found that interesting.